Hi, this is Eric with Math from the Gut, and welcome back to test driving the Pythagorean Theorem. Symmetry is an important idea in math, biology, physics, and many other areas. Let me introduce it with an example. As drawn, this square looks quite similar on both sides of this line. In fact, you might be able to tell just by looking that one side of this square is the mirror image of the other. To see this more clearly, we color one side blue and the other side red while still keeping the border, like this. Notice how both sides are identical and can be exchanged like this without changing our overall shape. Using technical language, we can say that the square is symmetric about this line. Just like our square that remains the same when we exchange its sides, we will now see if the length of the hypotenuse remains the same when we exchange the values of x and y. Put another way, we ask if the Pythagorean theorem treats x and y the same way when we're computing h. In other words, is it symmetric in x and y? Let's first think about what happens when x and y are swapped. Notice here how our distance x is the distance going left and right, while y is the distance going up and down, as usual. What happens to our hypotenuse h if we change things around, like this? Now you see that the distance x is going vertically instead, and y is now going across. How does that affect h, the length of our hypotenuse? Here, I'll do it again. Ready? Watch and see if h changes length. Also, does rearranging things like this make h change length? Let's do that one more time. So what do you think happens to h when we do all these things? Absolutely nothing. Hopefully you can see that h, the length of our hypotenuse, stays the same. In other words, it doesn't seem to matter whether the longer of the two legs is going across or up and down. So let's see whether the Pythagorean theorem tells the same story. We'll start with numbers. Let's say we have a triangle whose across or horizontal distance is 12 and whose up, down, or vertical length is 5. What is the length of the hypotenuse? So we start with the Pythagorean theorem. Note that x here represents the horizontal length and y represents the vertical length. So we plug in 12 for x and 5 for y and get the square root of 12 squared plus 5 squared. Doing the same math we did in section 2, we see that this equals this, or this, which is finally 13. So this is how things work for our original triangle. Now, let's interchange the horizontal and vertical distances like this. What does the math give us for h now? For this new triangle, we once again start with the Pythagorean theorem. This time, however, our horizontal distance is only 5 and our vertical distance is 12. Therefore, we'll end up with 5 squared plus 12 squared, like this. Doing the math, we get 25 plus 144 under the square root sign. But that still gives us 169 under the square root, which gives us the same answer of 13. So we get the same answer either way. Why does this work? It works because the Pythagorean theorem treats x and y in the same way. So it doesn't matter which of our two legs has length 5 and which has length 12. As long as one of them is called x and one is called y, we always get the same answer. You can see that the only thing that changes is the order in which the two numbers are added together. But the overall result stays the same like we would expect. Hopefully, you also see that the math we just did doesn't change when we do this, because our horizontal and our vertical distances have stayed the same. We still have 5 for our horizontal distance and 12 for our vertical distance. So let's say that a mathematically challenged friend tells you that this is the true Pythagorean theorem. What can we do to test this? Let's first try the degenerate case where the triangle is just a line that goes across with a length of 1. Like we discussed in the previous section, we expect the hypotenuse to simply equal the length of this line, or 1. Now, Let's try this out with our new formula. Using this formula and putting in the numbers, we get that h equals this. We're just putting in 1 for x and 0 for y in the formula above. When we do the arithmetic, we see that 1 squared is 1, and 2 times 0 squared is 0, so 1 plus 0 gives us 1 under the square root. And the square root of 1 is 1. So far, this other equation is working. But now, let's try the symmetric case where we go up by 1 instead of over by 1. Once again, we expect the length to equal 1 since we're now just looking at a triangle that's collapsed into a vertical line having a length of 1. Using the same formula from above and plugging in 0 for x and 1 for y, we get this. Now, when we do the math, we see that 0 squared is 0 and 2 times 1 squared is 2. When we add those up, we get 0 plus 2, or 2 under the square root sign. The important thing here isn't what the square root of 2 equals. It's actually a pretty ugly number that isn't just a simple counting number. The important thing is that the square root of 2 doesn't equal 1, since 1 times 1 isn't 2. So we are not getting our expected hypotenuse length of 1 here. Therefore, we know that your friend, as wonderful as he may be, is wrong about this equation. We also see that it's important not to get fooled into believing that an equation is true just because it works for one case like it did here. But it's also possible to see that your friend is wrong for another reason. We have just learned that the horizontal distance that we call x and the vertical distance that we call y should be treated the same way in our equation. Is that happening here? We see that both x and y are getting squared, so that's the same. But we see that y squared is getting multiplied by 2, while x squared isn't. For that reason alone, we can see that this formula shouldn't work. X and y are getting treated differently, but common sense says that they shouldn't be. And in fact, we can see that this formula isn't treating x and y the same way, since it gives a different answer for a horizontal line of length 1 than it gives for a vertical line of length 1. More generally, we have a horizontal distance of x and a vertical distance of y. The Pythagorean theorem tells us that h is the square root of the horizontal distance squared plus the vertical distance squared, which in this case is our familiar square root of x squared plus y squared. So this is the general result for our original triangle, where x is the horizontal distance and y is the vertical distance. Now, if we reverse the horizontal and vertical distances like this, what happens to h? After rotating the triangle, y has become our horizontal distance and x has become our vertical distance. Keeping that in mind, we start with the Pythagorean theorem again. But this time, the horizontal distance in our formula becomes y and the vertical distance becomes x. We're really doing the exact same thing here that we did when we were using numbers before. So when we make these substitutions, we get the square root of y squared plus x squared. Again, keep in mind that the first values in our equation are always the horizontal distances and the second values are always the vertical distances. But this, of course, equals the square root of x squared plus y squared, since it doesn't matter what order we added y squared and x squared in. And this is true regardless of what the actual lengths of x and y are. So you see that we're getting the same length for the hypotenuse for the rotated triangle in the general case, where we are using the general values of x and y to represent the length of the legs. Hopefully, the symmetry of the Pythagorean theorem is now obvious to you. If not, think about all of this a bit more. Symmetry is something that you can look for in many mathematical equations. So we're about halfway there now. I know that monotonicity, the topic in our next section, sounds like a scary word, but hopefully the basic idea isn't too spooky. In English, we'll be checking whether h increases when either x or y increase. Once again, please let me know what you think of these videos and if there are particular things you'd like me to cover in the future. See you in part 5.